forgot to record. I'm sorry. Okay, sorry to say that again. So welcome again to our class. And then, like I said again, homework for 1 week lab will be extended. I'll probably have 1 or 2 days deadline. Okay, so let's try to get it by Friday the latest. Okay, I'll give you one more day to work on it. All right. And the other thing is that we'll go over some of the basic stuff when calculating the moment of inertia on cracked sections, that is. And there was a mistake I think I made during yesterday's office hour. Unfortunately or fortunately, there's only one student who was influenced. But hey, Justin, if you're here and I see you just signing in, hey, Justin, just I saw you just signing in. So yesterday in the office hour, I mentioned that you can use the KD for the compressive reinforcement. That's not correct. And I'm sorry for it because I was distracted by a phone call. You know, this online meeting get a little bit messy. So I clarified that. And in addition, I upload an example about how to do compressive reinforcement to the canvas. You can see it. Okay. All right. So that's more like a general description. So let's get right at it. First of all, let's talk about the compressive reinforcement first. Okay. So let me share my screen so you can see it. So this is a hand workout example. And I just want to show you what it looks like. So I have a compressive reinforcement and I already uploaded to Canvas. So if you can now see clearly from here, you can also look up from your Canvas file, okay? But you can see that this is a rectangular section. And I have a compressive reinforcement to number 8 on the top, 3 number 8 and tensile reinforcement on the bottom. Height is 25 inches and the depth is 23 with concrete cover 2 inches. And the only difference between this section and the section we show in class is that we have a compressive reinforcement here. Okay. Now, like I said again, you cannot use KD for this case. You cannot use KD for this case. Okay. So you have to actually get the compressive reinforcement considered. How to do so is that since you have compressive reinforcement at the top, so you do that assuming you have uncracked section, the compressive reinforcement part. Okay. And by the way, this is for iCrack. Okay. This is for ICR. Okay. This is not IGT, but ICR. Okay. So when you have the compressive reinforcement, simply convert that into n-1 AS prime, that is compressive reinforcement area. And then you have the bottom bar, which is an AS. Okay. And from there, first thing you have to do is find the center, find the centroid, which is Y top, right? Y top, Y bar top. Here you use the equation we showed again and again, just find the area and the distance between each piece, the center of each piece to the reference line here. So we take in the reference line at the top as usual. We always take the reference line at the top fiber as usual, perform the calculation and show you that the 7.03 inch distance, that is the neutral axis, right? That is the neutral axis, is the distance between the neutral axis, the top line here, and that is the reference line. Okay, that is the reference line here. All right, so that is Y bar. And how to find ICR afterwards, right? So have the compressive zone, you find the moment inertia of itself, and have A, which is area, and Y, the distance between the center of the compressive zone to the neutral axis, and do the AY squared. Okay. Now notice that for a top reinforcement, the compressive reinforcement, this little bitty wings on the side on the top. Okay, and thus you don't have to worry about the moment inertia itself, which means I itself has been ignored, but you still have to consider the area and the other distance and squared. Okay. So for the bottom reinforcement, similarly, you ignore the moment inertia of itself, but taking into consideration the A, the Y, AY squared, okay? And then you sum them up, and this is what you end up with, okay? This is what you end up with. All right, so this is how we do for a compressive reinforcement, okay? Since I have already uploaded to Canvas, so I don't want to spend too much time on this, please review after class and let me know if any questions on this, okay? All right, so for now, any quick questions on this? Guys, any quick question on this? Okay, all right, so again, yeah, go ahead, Mike.
How does like a I-beam or a T-beam affect it compared to like a normal like rectangle beam?
Okay, so for I-beam and T-beam, let me share my screen. Let me draw it actually for you. There's not much a difference, actually. Okay, there's not much a difference But instead of doing the two-piece thing like we did for rectangular, you have to do multiple pieces. Okay, you have to do multiple pieces. So let me show you, okay? So this is that. Okay, all right, so let me just do this first. Okay, so for example, if I have a beam, okay, and this is the I-beam, all right, I still have to do two stage, the uncracked stage and the cracked elastic, okay, cracked elastic. Now for the uncracked stage, say I have 3 bars at the bottom and 2 bars at the top, right? So for the uncracked stage, I simply need to do what? I need to, let me just copy this. Okay, for uncracked stage, okay, uncracked. What I would do simply just remove these bars, okay, remove these bars, okay, and convert them into a little bit wings on the side like this, all right, like this. Okay, since it's uncracked, so this area will be n minus 1 as. This is as. This is as prime. And this will be n minus 1 as prime. Okay, and you just proceed as it is the old-fashioned I section and do the moment inertia accordingly. Okay, so if it's cracked though, if it's cracked, so let me just do this. Okay, so if it's cracked, then you have a different scenario. That means, okay, you have to find the neutral axis first, but before you do that, right, you take this out, you take this out, okay? Now this at the bottom here, since it's cracked, so this will be N AS, and this tiny wing here on the top will be N minus 1 AS prime, and then the neutral axis will be sitting here. So you only have to consider the shaded area like this for your moment inertia. All right. Okay, is that clear? Is this clear, Mike?
Yeah.
Okay, good. So this is correct. All right. So this is for T. Well, this is for I. Then T beam is similar. T beam is similar. Okay. And you can go over the example I posted to Canvas and try to just walk through it because you see a problem like this in the exam for sure. Okay. You'll see a problem like this in the exam for sure. Okay. Now, yesterday in the office hour, I only have 2 students walking in, okay? Now I assume you guys got 3 students walking in, okay? I assume most of you guys are good, but still, you may want to pay attention to this cracked and IGT, okay? Because you have this in the exam, okay? You have this for the exam. All right, so while we're at it, okay, let me make sure this is lecture 22. So let me just make sure this is lecture 22. I don't want to do this. Lecture 22. Okay. All right, good. So before we go into the deflection, which is today's main topic, okay, I just want to talk about the one-way slab a little bit more, okay? Now, recall from the homework, now this is the mini slab, I call it, okay? Just give you some illustration, mini slab. All right, now I have a columns here, columns here, columns here, I suppose columns here. Okay, and I also have columns here, columns here, columns here, columns here, correspondingly here, I think 3 spans. So here, 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 somewhere like that. Right? These are my column lines. Okay. Now, on top of this column, this is called the main beam or called girder. Okay. These are the main beam or called girder. Okay. And then we also have these tiny beams in the middle, and those are the just beams. These beams does not sit on column, but they're there. They're there. Okay. And again, we have the other direction. Okay. Well, matter of fact, let me make it easy for you. Let me just use a different color for the other direction. Okay. This is blue. This is blue. This is blue. This is blue. All right. And you notice in the problem, in the homework problem, there's a shaded area which showing you the strip. Shaded area which showing you the strip. Okay. And this is about 1 foot, right? This is 1 feet. Okay. This is the strip for design. Strip for design. Okay. The common mistake I've seen is that people confuse which direction we're talking about. People confuse which direction we're talking about. Okay. So I'm just gonna label this as 1. This is 1 prime because it's in the middle, and this is 2. This is 2 prime. It's in the middle. This is 3. This is 3 prime. Again, this is in the middle, and this is 4. Okay, so when we talk about the span, right? When we talk about span, let me use color red. Okay, we always do a cut like this. Okay, do a cut like this. So you see it from this way. Okay, you see it from this side, and what you actually see is this is the span. So I have 1. Okay, I have 1 prime. Keep going. I have 2. I have 2 prime. I have 3. I have 3 prime. So this is not right. I need to extend it more. Yeah, this is right. So 3 prime, and this is 4. Okay, this is the core section. This is the core section. So when we talk about moment coefficient, when you do the homework, do moment coefficient, right? Use a blue color. So this is the slab that we're talking about. You have support here, support here, support here, support here, support here, support here, support here. Okay, and those numbers, right? For example, 1/24 minus something like a in the middle is 1/16. I don't remember the number. Okay, I'm just drawing out loud here. Minus 10, minus I don't know 11. In the middle, 1/16 again, etc. So on and so forth. This moment, okay, this moment if I really want to draw it out, okay, say for example, this minus 1/24, okay, I'm going to use blue here. So if I want to draw the moment out on the section here, okay, the moment is actually negative, so it's the other way, like this sign, and this is what it is. Okay, omega UL squared. Okay, you see this moment? Okay, this moment looks like that. All right, so since this is side view, say I want to do a longitudinal, I want to complete the 3D view. Complete the 3D view looks like this. Okay, now along this span, right? Along this span, let me use red. So this is A, B, C, D. Okay, along this A, B, C, D span, okay, they're all minus 21. That means if I do a cut, okay, cut of the slab, that is, if I do a cut, you see this moment consistently acting along this direction of minus 1/24 omega u L squared. Now this 1 foot of strip is basically per strip like that. Can you see it? Okay. So these moment distribution we're talking about is in along this direction, along this 1, 2, 3, 4 direction, not the ABCD direction. So when the problem is asking you, okay, for example, at base 3, what is the moment coefficient? It's asking you about this point here is a minus, for example, 1/10. I'm just making things up, okay? Minus 1/10 omega u L squared. It's asking you what is the moment here along this line here, okay? And they're same. They're the same. Now, yes, A, B, C, D are here. So along this direction, you have A, B, C, D. I have three. Sorry, you have 3 spans, right? You have 3 spans. 1, 2, 3, something like that. 1 bar, 2 bar, 3 bar, differentiate. Okay, so you have 3 spans, but these 3 spans has nothing to do with the moment coefficient this way. In other words, when you're trying to evaluate whether you can use moment coefficient or not, you are going to use geometries only along the 1, 2, 3, 4 span direction. That means you need to care about this, you need to care about this. For example, if the question asking you bay 3, you only care about this span length, for example, this is Ln left, I call it Ln right. You can call it 1 or 2, doesn't matter, but Ln right divided by Ln left has to be smaller than equal than 1.2, the 20%. Okay, so that is the geometry you are taking consideration when you say or when you judge whether you can use moment coefficient or not. Okay, so this is the common misconception I've seen so far. Okay, so get this picture in your head when you do the exam and make sure you know which direction is the bending direction. Okay, which direction is bending direction. So any question on this, guys? Are we good here?
So I have a question, Bob.
Yes, sir.
So on like homework 8, when it
Mm-hmm.
asks like number 3,
Mm-hmm.
so we shouldn't be doing like a completely separate like ACI moment coefficient for across that 3-span beam. They're
No,
all just exactly the same.
they are just not exactly the same, but they're just going to be this direction.
Right. So it'll be the moment will be uniform across that like
Yes,
3-span.
yes,
Okay.
yes. That's the confusion, right? It was asking you about along this, it says continuous span, but actually that is the transverse direction. That's not the longitudinal direction of the one-way slab direction.
Gotcha.
Gotcha. Right, good, good. Okay, that's the confusion. Okay, good, good, good. Okay, so you see, we have to clarify on this. Okay, we have to clarify on this because in the exam you only have one-way slab. It is now two-way. Okay, I keep saying one way, one way. What does the one way word mean? I said it in the lecture, but and also draw the drawing. Remember, I show you the slab that I said this shortest span give you the bending. When we say one way slab, that means the slab only bend in one direction, along one direction. Okay, you only have moment this way. The other direction, not much moment, not much moment. It does not sag, it does not bend that way. Okay, very important. So this is the one-way slab. Now in the two-way slab, you have a different scenario. You have to do the weight distribution line, moment, plastic moment line. That's a complete different story. Okay, this is one-way slab. All right. Okay. Any questions on this? It's very important because we have a full problem like this in the exam. It's not going to be multiple choice. Okay, it's going to be right out. Okay. Any questions on this so far? I got to make sure you guys are clear. Are we good? All right. So I'm going to extend one more day on the one-way slab homework. So you have one more day to review this and redo it if you made a mistake there. But in the exam, we will see almost identical problem, just like the slight change of geometry, slight change of the loadings and span lengths. You just have to do the whole different setup, but the concept is identical to this, okay, to the homework. So make sure you know how to do it. Okay. All right. So let me quickly talk about the exam. The exam is going to be next week. Okay, exam is going to be next week. Now, I'm making the exam right now and discussing with Dr. Snee what kind of problem we're going to have on them. But from what I see right now, it's going to be all solution problems almost. Okay, not a whole lot of multiple choice. Okay, so that rules out the luck out of it. And in terms of format, we're leaning more towards online again. We're leaning more towards online again. So not probably gonna do in person for this, okay? Just because of the situation. All right. So you have time to study for it, and there will be 4 problems. If we all convert them to solution-based problem, each problem weighs 25%, so it's pretty heavy. And you have to know how to do it from beginning to end because partial credits is important. Okay. So make sure you go over the lecture notes, go over the homework, and ask me questions. I'm gonna run a mini review before the exam, hopefully next Monday or tomorrow. Okay. But you got to make sure you review them properly. Okay. All right. I'll let you know more when I know more about the exam. All right. But that's what we have so far. Okay. Any questions about the exam? Any question about the second exam? Oh, we all quiet? We're good on it? All right. Okay. So I'll let you think about it. If you have any question. Yes, Steve, any question for me?
Is it gonna be the same like time frame then too, or is that going to change if it's one more solution problem, anything like that?
That's a good question. So we're still making decision, but seems like we're leaning towards the same time frame like we did in the first exam. So we'll design exam to be finished in 1 hour, but you have 3 hours to work on it, just considering all the situation going on. Okay. But if anything changes, I will let you know. All right. Okay. Anything else, guys? Are we good? All right, it's critical, okay? The second exam is critical. So I really suggest you start taking a look at what we have talked before and ask me questions, clarify things, okay? So one more thing before I get into the main content, it seems to be a short class today anyway. So the exam is gonna cover, right? Think about what we learned so far. The exam is gonna cover shear, okay? It's gonna cover shear, right? The whole thing, the shear design and everything, the one-way slab, okay, and actually before that, before the shear and one-way slab, there's irregular section, right? There's irregular section, okay? Irregular section, shear, one-way slab, and we also talk about serviceability, right? In terms of IGT, so let me be more general first. So serviceability, okay? That is in terms of IGT, I crack, okay? These are the four main components we have covered so far, okay? Now, today I'm going to talk about deflection a little bit. Due to the time for it, you will not be tested on actually deflection calculations. It's mostly just going to be IGT and ICR, okay, for now. Again, if anything changes, I'll let you know. But these four are the content that will be covered in the exam, okay? Covered in the exam. Okay. All right, so time for us to review, all right? So we'll talk about this either tomorrow or Monday. We'll have a mini review session about it, okay? All right, so let's get back to the main course today, right? Main course today is lecture 22. We talk about deflections. And this is also serviceability, and we're going to talk about how we're going to calculate deflections. How we're going to calculate deflections. Before we start, let's take a look at the structure analysis, shall we? Structure analysis. So we have a simply supported beam, for example, and this has a distributed load on top of it. And let's just say I have omega u and sit right here. And then I also have the other beam, identical but constrained at both ends, fixed. Okay, and it's sustaining the same load. Okay, sustaining the same load, omega u. Okay, and I'm trying to get a deflection out of it. Get deflection out of it. So simply from simply supported beam, right? Simply supported beam. This is the original shape, and after I apply loading, it deform like this, And in the middle span, this has a maximum deflection delta mid span. All right, and we all know the calculation equation for it from structure analysis is 5 omega u L to the power of 4 divided by 384 EI. Okay, and for a fixed support, we also know the deflection shape of it, right? Profile of it. It stays a little bit horizontal at the beginning, has a little bit deflection, then goes back, right? So at the middle span, in this case, it's much smaller. It's much smaller, right? And the number is omega L 4. This is U, this 384 EI. You notice that this is 5 times smaller, right? This is 5 times smaller. All right. What does it mean? What does it mean? It means that the boundary conditions or end constraint matters. Okay. So this means end constraints matter in terms of deflection calculation. Not a question mark. Okay. Sorry. In terms of deflection calculation. Okay. In terms of deflection calculation, it's important. Why I bring this up? Because let's take a look at a beam. Let's take a look at a beam, right? So in a real beam scenario, I have a rectangular section. Okay, rectangular section. This is awfully small. Sorry about this. Let me draw it bigger. A lot bigger, right? So I have a rectangular section and I have a simply support condition. All right. And if I assume I have a distributed load, right? So let's assume I have a distributed load. So let's just do a distribution like that, uniformly distributed. Okay. Omega U. Seen this a lot. Sitting on it. All right. And then once I deform it, I will start to see crack. Right? We talk about this flexure and shear cracks in the middle. Okay. Flexion shear cracks in the middle. Okay. But no cracks at the end. No cracks at the end. Okay. So at the end, I have intact sections. Intact sections. All right. So what's happening here is that if I take a look at the moment diagram, right? So I just label the two ends, draw my moment diagram, right? And the moment diagram looks just like this. So this is my moment. And since it's simply supported and uniformly distributed, I have a parabolic line. Okay. Now, why you see crack? Because now here, this is the cracking moment. And here, this is the cracking moment. Okay. That means, right? That means, of course, this is MA, the maximum moment. Okay. And that means in the middle, this is cracked. In the middle, this is cracked region. And we have to use ICR. Remember, we have to use ICR. Remember, and on the outside, this is uncracked. And we have to use IG. Okay, we have to use IG. All right, so this is, sorry, AGT, okay? This is the reason that we have to consider both segments. One is in stage 1, this is in stage 1, and this is in stage 2. Right, stage 2. So what we're going to do is we're going to convert, right? We're going to convert the two sections, right? Because now if I take a look at it, the effective section that if we're going to treat, if we treat the section to be the same across the span, if we treat the section to be the same across the span, that means let's use a effective moment of inertia called effective moment of inertia. All right, so let's just say I'm just going to treat it as a 1 ICR, right? So sorry, 1 IE. Now I don't know what it is, but I'm going to define it as effective moment inertia. Okay, and turns out, I can get this from ACI, and ACI there's equation for it. The I effective equal to MCR, cracking moment, divided by MA, which is the maximum moment across the section, okay, to the power of 3 multiplied by IGT, okay, plus bracket inside 1 minus MCR divided by MA to the power of 3 and bracket outside ICR. Okay, so this is the equation that ACI uses to calculate the effective moment of inertia, and you can find this from ACI 24.2.3. Okay, 24.2.23, sorry. Okay, now MCR is the cracking moment. So I can write down MCR equal to FR modulus rupture multiplied by IGT divided by YT. Okay, and MA is applied moment. Okay, applied moment. In this case, it's a maximum moment, right? Maximum moment. Okay, and IG is the uncracked section, right? Uncorrect moment of inertia. Okay, and ICR is the correct moment of inertia. Okay, so this is the equation to calculate the effective. This is the equation to calculate the effective moment of inertia. Okay, but now this is for what? This is for a simply supported condition. This is for simply supported condition. So let me write it out here. So this is for simply supported condition. Okay, simply supported condition. So simply supported. Okay, simply supported. All right. Now, why I mentioned this? Because for continuous is different. For continuously supported beam, the equation is different. The equation is different. How so? Because now if I have a continuously supported beam, right? For example, I have a column here, and this is my beam, and it's fully joined here, and this is column, and suppose my beam can extend further than that, right? But now, if you take a look, right, the moment diagram for this, is different from the simply supported case. The moment diagram for this is going to look like something like this. I have negative moment at the support, and I have positive moment at the middle span. Okay, so I have different bending moment at different bending moment. Now you may say, oh, what's the big deal, Bob? You know, they're just different bending moment, right? They're just different bending moment. It's hard to imagine that I changed the section just for that. What I'm saying is that, you know, I would think the beam have the same section. Yes, that's correct. The beam will have a same section. But if you take a look at it, say I'm gonna make a cut. Let's make a cut in the middle, right? So let's make a cut in the middle span. Right? So I can see, assume I have a rectangular section, okay? Now to make it complicated, I have a rectangular section, right? So this is my rectangular section. Since it is in the middle span, right? So the tension reinforcement is gonna be here at the bottom, and the compressive zone is gonna be top. So this is the compressive zone, concrete compressive zone. Okay, so this is not a big deal. We all know this, right? And you calculate the moment inertia using this section. However, though, for the negative section, right? For a negative section, right? This is the negative section, right? You do not have that anymore. Your compressive zone is at the bottom. Although the tensile reinforcement you may see become compressive reinforcement, and the compressive reinforcement you see now become tensile reinforcement. Okay, what does it mean? It means that I have to compute them differently. So looks like the same section, but when I compute my moment inertia, I have to compute them separately. Okay, now to differentiate them, we actually have name for them. So this is called I effective midspan. Okay, and this is called I effective 1, means on the left end or one end, and this is called I effective 2 at the other end. All right, so now for this case, the effective moment inertia I effective becomes different. So for continuously supported beams, I effective becomes 0.5 IE midspan plus 0.25 IE1 plus IE2. Okay, and just to make it clear, this is the moment of inertia at midspan. Okay, and these are the moment inertia at ends, two ends. All right, so that's how we're going to calculate moment of inertias for continuously supported beam. For continuously supported beam. Okay. Now we can take a look at an example, right? Can take a look at an example. Okay. So let me show you what example, right? Show you one example. Okay. So let me zoom in. Oops, different color. Okay. Show you an example. So example. Okay. So the example is a column and beam structure, right? So the question is for the beam below, first calculate the effective moment of inertia. Okay, and now let's take a look at the section, right? So I have a column look like this, and the beam just continuously supported, and I see another column and extend it out, and then here is the other part of it. Okay, column beam structures, right? And I have reinforcement in it too, right? I have reinforcement in it too. And this is a little bit tricky, right? This is a little bit tricky, but before I draw reinforcement, I forgot, let me draw some dimensions, okay? So the clear span between the two columns at 25 feet. Now, from center to center, this is 26 feet, 26 feet. All right, so let's take a look at the reinforcement, right? Let me use black color to show the reinforcement. Now, in the middle span here, it is going to be positive bending moment. So I know the reinforcement is going to be at the bottom. And then I extend my reinforcement across it, so I have more bond development lengths. We have more bond development lengths. We'll talk about that later, next lecture. But that's my main tensile reinforcement, okay? And these are two number 8 bars, okay? Two number 8 bars. This is a side view, right? You don't see the other one that in an outside plane direction, but this is two number 8 bars. And just to reinforce it, just to provide enough reinforcement, on top of it, I'm gonna, oh, sorry, different color. On top of it, I'm gonna provide an additional reinforcement, and this is two number 9 bars. And both of them are in positive bending, right? So I'm gonna circle this out. Yeah, I'm gonna say this is positive reinforcement. Okay, positive reinforcement means that they're taking care of the positive bending moment, positive bending moment. All right, now since it is a continuous beam, I'm gonna have reinforcement, right, for negative bending moment at end, which means the reinforcement gonna be on top. Reinforcement gonna be at top, right? So I have reinforcement here, and then these are 4 number 9 bars and 1 number 11 bars. It's quite a bit. And same thing here. This is 4 number 9 bars, 1 number 11 bars. Pretty big. So I call this negative reinforcement, right? So these are neg reinforcement. This is neg reinforcement. All right. Okay. Now, just in case you haven't seen clearly, right? So in the middle section, right? So in the middle section, I do not have any compressive reinforcement. I just have 2 number 9 plus 2 number 8. 2 number 9 plus 2 number 8. Okay, but at ends, I have 4 number 9, 1 number 11, but be careful, I do also have this 2 number 8 as a compressive reinforcement for the negative bending moment sections, Okay, so these are my reinforcement configuration. Okay, so what the moment looks like, Now, for the sake of time, we're just going to show you the moment diagram, okay? Just going to show you the moment diagram. So now, simplify the structures. I want to simplify the structure. I say, look, cut it here from clear span to clear span, cut it here, okay? And then I have a beam. And now I draw the moment diagram, okay? And this is the parabolic. try my best to draw a parabolic. It's a little bit shaky, but looks pretty good. And now I have the moment here, which is minus 225 kip feet. So it's minus 225 kip feet. What did I tell you? A negative moment, negative bending moment. Okay. At the top here, I have 162 kip feet of positive bending moment. Okay. And just in case you forgot about it, this is IE2, right? This is IE1, and this is IE middle. Okay, IE middle. All right, so this is the bending moment. This is the bending moment. All right, I only have 5 minutes, so I want to stop here. But before I do, let me quickly run over it before we go on, right? So after you've seen this picture, right? After you've seen this picture, I have IE1, I have IE2, I have IE mid. So we are going to determine IE middle first, and IE2, IE1 correspondingly, then get that IE, right? Remember the equation here? We're going to use that eventually. But before we use that, we have to do this first, right? We have to do this first. Okay, so we're going to show you next lecture how we're going to combine this equation right here and this equation right here to get effective moment of inertia, Okay, all right, so I'm going to stop here. Do you guys have any questions for me on this? Any questions?
Back up to the IE